Hello, all. Now let us see the concept of law of conservation of angular momentum. In the law of conservation of angular momentum, first of all, we need to look at the statement of the system. According to law of conservation of angular momentum, for an isolated system, if external torque is equal to 0, then the angular momentum remains same or fixed quantity. So how do you consider this particular statement? See, let us see the proof. According to the problem or according to statement, only one line derivation here. External torque is 0 na? So external torque is equal to 0 means according to definition of torque, we have dl by dt is equal to 0. This is possible if and if only L is equal to fixed number. L is equal to fixed number. So change in L becomes 0. That means L is nothing but always a constant quantity. They won't change. Therefore, L must be is equal to either L initial must be is equal to L final before and after. So in such a case only, this law of conservation of angular momentum is valid. Now, what are the applications of this law of conservation of angular momentum? Let us see one by one. According to law of conservation of angular momentum, we have I1 omega 1 is equal to I2 omega 2. Very basic concept. So initial value must be is equal to final value. Imagine that a particular object is rotating about its own axis and making rotation like this. Under such a case, initial moment of inertia is I1 and final moment of inertia is I2. Angular velocities are omega 1 and omega 2. On such a case, we have the side important formulas. I1 F1 must be is equal to I2 F2 and I1 by T1 must be is equal to I2 by T2. Second interesting thing is that in such a case, suppose during the rotation process, if some amount of mass was lost or melts down, anything was happened. Under such a case, frequency of rotation altered and inertia also altered. Best examples here nothing but a man rotating on a disc. So this is the disc. Imagine that there is a person. Initially, he flips his arm like this, and after completion of some time on the rotating disc, if the same person folds his hand like this. So during these two cases, definitely the number of rotations made by the person also changes. That's the logic we have to follow here in the first case. In the second example, let us try to consider there is something like a disk, a big solid disk. This particular disk contains mass of capital M, radius of capital R. Now, imagine that there is a small chunk or a small lump of mass M having initial velocity u. It is just simply traveling along the tangent to the disk. Okay, tangent to the disk. During this case, simply this sticks to this particular point and then combinedly rotates. Then we need to calculate what is the common angular velocity for this particular system. Now in the given case, while lump is going on like this, is a tangent. So this particular lump simply attached at this particular point. In this case, we have to apply the same condition. L initial must be equal to L final. L initial means capital M, which is at rest. Therefore, initial value is 0. omega value is 0 and radius of, so for disk it is mr square by 2 we can write down. So initially at rest we can take, it is not rotating initially, and then it is going, so therefore initially just before the common contact, angular momentum of the lump is nothing but mu into r, which is equal to, after completion of rotation, mass of the disk everything is same, therefore mr square by 2 plus lump contains moment of inertia of small m into r square whole of omega common. I am using formula here, I into omega common. Upon solving this, we have omega common is equal to this m u r divided by, we can make down as m by 2 of small m into r square, we can write r square gets cancelled, and the final answer goes to, okay, 2mu by capital M plus 2 into small m into r. So this is the final result for the second case. Let us see one more condition. Point number 3. Imagine that there is a rod like this which is fixed at the one point on the horizontal frictionless plane, and imagine that a small mass m which is going like this and attached here and commonly rotating. In such a case, same to same, mass of rod is m, length is l, mass of chunk m already given, and u is nothing but constant speed going like this. After then both are rotating. Then in such a case, mu into radius of rotation is nothing but L here into moment of inertia of rod about the point is nothing but one corner is m square by 3 plus m into L square of omega common we have to write down here, and then omega common is given by mu into L divided by capital M plus 3 into small m, and whatever the LCM 3, this goes to numerator and we can make L square as common, and then answer is 3mu by capital M plus 3m into L, what we write down here, the third case. Now let us see the fourth condition. In the fourth condition, something it is interesting thing. Imagine that there is a something like a rod and this is the center of mass of the system. Now if a mass of m going in this direction with the speed of u and another mass of identical mass or identical block you can take moving with the same speed u in opposite direction like this, such that the system is pivoted at the center of the system or center of the scale. Now after interaction what happens, all the things are combinedly rotating about a common angular velocity which is question mark, we have to find out here. During this particular condition, initially how many objects are there? 3 objects. Therefore for rod it is 0, very interesting thing. Second thing is, for rod it is 0. Second thing is upper mass, that is nothing but mu into L by 2 plus second mass, bottom mass, mu into L by 2, where L by 2 is nothing but radius of rotation here. At the initial condition, what happens, this total length is nothing but radius of rotation, whereas present problem gives that because it is pivoted at the center, therefore we have radius of rotation becomes L by 2 for here and L by 2 for the bottom one. That's the logic, which is equal to, what is the moment of inertia of the rod? ml square by 12 plus 2 into m into L by 2 whole square, because two identical particles are symbolized, and then we have omega common. Now we have to find out omega common here. Omega common is equal to, upon adding these, what we have is mu L divided by ml square by 2 plus ml square by 2, we can write down here. Upon solving this, we'll get the final answer in this condition. Now let us see the one more application. Point number 5. At this case, now we have the same rod like this. Here a mass of small m is moving with the speed u and attaching here, and another mass of, here it is m1, Here another mass of m2 moving with the same speed attached at the end such a way that this particular rod does not have any kind of pivotation point. So it is not pivoted, so it is free to rotate. How we can rotate, we got it out. In such a case, imagine that mass of m2 is a little bit more than m1. That's a condition given. That means this is the heavier block, this is the smaller block. Therefore, the center of mass of system will be neighbor to that of heavier mass. Therefore, imagine that this is the position of the center of mass and this is the original center of mass. So, we need to find out this particular gap as nothing but what? X. Let us try to find out this particular distance. Okay, so this particular distance nothing but r1 and this particular distance is nothing but r2, where r2 is equal to radius of rotation. R2 is equal to opposite mass by summation of masses into total length of the system. What's the total length of the rod? L is the length. This is the center of mass location. And R1 is equal to similarly opposite mass by summation of masses into total length. So by using this you can calculate R1 and R2. Now let us try to apply law of conservation of linear momentum. Under such a case, initially rod is at rest. So therefore we can't do anything for rod. And what we write down here, M1 R1 into U plus M2 R2 into U, which is equal to moment of inertia of the rod about the point X, not the center of mass. About this particular point only rod is rotating. So therefore, at this particular place, ml square by 12 plus m into x square parallax theorem together with, you have to use moment of inertia of these two things. That means m1 r1 square plus m2 r2 square, the whole into omega common. So upon solving this, we will get omega common for this particular picture.